All right. So here we're talking about basically resonance, mostly just practicing resonance and addition reactions. So H plus can come here, right? So I gave you three products. The one thing people could have done that might have been helpful is looking at A, B, and C. And what you can do is maybe think about what if I just like cut this off here, cut this off here, cut that off there. What happens then, right? This atom, and this atom had to be carbocations, right? Because that's originally, right, with H plus, you recognize these things, that's where the solvent added. So you can take like one step back from A, it would look like this. Like, well, how can I make this carbocation? Then you go up here and say, well, if I pi bond reacts, I can put the plus charge there. And then the solvent can add and make A. Right? So that's one of the things maybe some folks figured out. It's called retrosynthesis, like working backwards, and how this could have happened. So B would have came from, let's see, let's find out where B's at. So this is what B would have had been look like this, right? So that would have been from the H plus adding, but instead of going to the least substitute side, it go to the more substitute side. And now the reason why I would do that is because this is secondary, but it's secondary and allylic, right? Pi bond resonance, right? That is more stabilized, that's pre-stabilizing. So that could add there, and that would get you B. Now we still got to find A, so we could, to do A, we do a resonance, another resonance, and that gets us to this carbocation, which is the other one we're looking for, right? Solvent adds, proton transfer. So while a challenging problem, the thing I was hoping people would see, I tried to look at was, where did these things come from, right? Where did they all come from? Why is the all right, so this one, terminal alkyne, organolithium, C minus is going to deprotonate a terminal alkyne, or it's going to deprotonate terminal alkyne to make it C minus with an alkyne. That's product one. Now we're going to introduce it to an epoxide. All right, that epoxide, right? So we got to decide acidic or basic. Carbon with a negative charge. These nucleophiles, if the nucleophile has a negative charge, it's basic conditions, which means we go to the less substituted side of the epoxide. So we draw, so the way I draw epoxides are these three-membered rings. We did this with bromonium ions or mercurium ions. I like to draw it so the three rings in the plane. So there's wedges and dashes. And so in this case, there's two H's here and one H there, and this is help us understand that this is the less substituted side. So we don't have to draw those H's in. They don't have to be there. But it helps us signify that this was a trans addition, but they don't have to be there by any means. So then you add into the less substituted side, basic conditions with epoxides. Make an O minus. It reacts with something. In this case, it's H plus. Makes the alcohol. And then we keep the wedges and dashes the same. They don't need to change here, even though we're doing SN2, because, right, the things are ending up on opposite sides. The OH and this alkyne piece are they're signified as being on opposite sides. Last one here, same reactant, different nucleophile. So same electrophile. So we have a ketone and an ester, okay? So we gotta look at Mont Carbonyl, and then we look at what kind of reagent, what kind of nucleophile we have. We have sodium borohydride, lithium aluminum hydride. Well, we know this is less reactive. We know this is more reactive. This will only react with ketones, and it gets its H from the solvent. So that would give us this alcohol product. Lithium aluminum hydride, right, there's four H's there. It adds in, makes an alcohol. And esters will add in, up, kick out, and add in again. And you get a triol here. And then the last step is H plus protonates everything at the end. But you got to make sure there's two different steps there. All right, let's walk through the mechanism. I'm not asking for the mechanism, but we can walk through it to help figure out what the product is going to be here. So we have lithium aluminum hydride, which we know, right, will react with ketones and esters. So we have a ketone, we have an ester. Ketone's most reactive. Let's have that react first. So H minus is going to add. All right, we're going to do addition step. And now we have tetrahedral intermediate. I guess we added the H, so it's there. There's no good leaving groups, so we're done. That's it. right? H and carbon are not good leaving groups, so we stop. Now, remember, lithium aluminum hydride has 4 hydrides, so we can add in another H minus whenever we want, right? Now it's going to go for the ester, so it's going to add in there. And again, nothing's changing up top. We added 1 H in. So now we have a tetrahedral intermediate. But in this case, we have a good leaving group, right? Ester has a leaving group. So we're going to do an elimination. Right, so here's an addition. But now we can kick out that O, right? So we're making O minus. And we actually have an aldehyde here, right? And aldehydes are super reactive, so another H minus is going to come along, and we're going to add in to the aldehyde. So it's like we're collecting O minuses almost, but trust me, this is what will happen. There's an O minus there, and now there's another H. There's 2 H's. No longer have any good leaving groups, so now we're done. And so the last step, now we're on to step 2. Everybody goes and gets an H. And that gets you to the product. Right? So it's really understanding types of reagents, how it's reactive, and then, right, remembering, right, some of these carbonyl groups like esters and hydrides, acid chlorides, have leaving groups, right? And so they'll leave. So you'll add something in, and then you eliminate, and you can keep adding things in. Especially with the sodium borohydride and lithium aluminum hydride, they have 4 naturally built-in H minuses.